Okay, we are live again. Welcome to another episode of Bitcoin class with Satoshi. I'm here with Dr. Craig Wright, is the inventor of Bitcoin and also the chief scientist for Unchained. My name is Xiaohui Liu, and I'm a creator of SQL. And what are we going to talk about today, Doctor?
Okay, so shall we? We're going to continue talking about the same sort of topic, but extending it a little bit further. Now, as I'm doing that, the other aspect, as I've been saying, is to get people to think beyond just on-chain exchanges into SPV and how they can now utilize transactions, not just by looking at the blockchain, following a blockchain explorer, but even having transactions that have embedded outcomes that can one by one update a system. So each time we send a new state or new input to some transaction, now having some sort of fixed transaction type that allows us to control the outcome for the next sort of clock cycle loop, etc., that we want to do.
Yeah.
Now, that even can be more difficult for people to track or attack or do anything to, in that we don't even need to have linked transactions. So most people think that everything on chain needs to be directly linked.
Okay.
Like you need to be able to follow transaction to transaction to transaction.
Yeah,
But the logic can be taken off-chain into another device.
Okay.
We can have a provable computation of some value, and that can even use the on-chain information in a way that the machine can verify, but move away from sort of publicly.
Okay.
Now, we talked about doing things like number 42s and hierarchies of keys, but we can also do the same in hierarchies of off-chain calculations that use the calculated keys.
Okay, so I think this is not a concept I've heard often, so can we elaborate a little bit more?
We will. So let's take it down to something completely not complicated at all, and think about the fact that we can add ECDSA keys.
Yes, yeah, private keys, yes.
Yeah, so if I have a public key that belongs to you, I don't know the secrets, but I can send a message to it.
Yes.
Now, imagine that I want to be able to do something to prove that a transaction originated from another transaction that I know about, that it links to that, that I have a value of state that is stored on chain from something else. Now, the simplest way of looking at this is a UTXO is a 256-bit value.
Okay, you mean transaction ID?
Which also happens to be the sort of length of a key.
Is this like a coincidence? Is it like a design choice or?
Oh, it just makes things a bit easier, especially when I'm explaining all of this. We can actually extend that out, which we will in a moment. But now consider that that now allows us to have Xiaohui's key plus a value that we can calculate from a particular UTXO.
Okay. So this, I think, what do you mean by you can have a on-chain data linked, but not necessarily linked through transaction?
Take the UTXO, the 256-bit of public information, and multiply it by the curve point G. I now have a public key that anyone can calculate. Let's call that PB. And Xiaohui's main key can be PA.
Okay.
Who can solve PA plus PB?
Yeah, just me, because
just you.
Yeah.
So
Only
that's
have
not
the,
terribly, yeah, that's not terribly private yet, because if I know what a UTXO is and I know one of yours, well, I could data mine the whole lot and try and find all of the keys that might be yours. Correct?
okay. You are saying, okay, this one I don't get it. You have the sum, right? But how do you
Yeah, but
get
I
from the
mean,
sum to the,
anyone can calculate at the moment the UTXO to get a key value to add to your key.
yes.
So anyone can go out there and calculate all the, I mean, if they've got a big enough computer, they can calculate. So I'm not saying everyone can, but some people could go out there and calculate all the possible keys that you could get just because they can.
The key, for example, in this case, I have it's almost like I have a master key somewhere or identity key, so they can all derive my public key. There's a plus with this
Yeah.
UTXO key. Okay.
Hmm. So people could go through and try and find out your original key by either summing or subtracting values. Now, let's take it one step further. Remember, we can have a Diffie-Hellman calculation between the key values. So now what you can do is take that value and either XOR it or add it or use it in a HMAC. I won't even guarantee which way you want to choose because there are many ways of doing it.
Just masking to me. It's like you have how you mask it.
We could
matter.
encrypt it using AES that the two of us know. Now that then creates PB that is not determinable by anyone but you and I.
Yes.
So if I'm sending your machine information and you're watching this, or getting an external alert, you now have something that you can calculate. And it doesn't even need to be from my original sort of stream. So I could, you could even be watching this original UTXO and see it spent, but get paid from another UTXO and be able to work that one out.
So the UTXO, you mean the UTXO I derived this kind of a mask public key from? Okay, now have it's being spent by this okay. So does this UTXO belong to either of the party or who
someone has to be
controls it?
able to, I mean, someone has to be able to do something with it. So generally speaking, if you're saying if it moves and you're watching it and it moves, or I don't need to be in control of it, but someone under that I'm associated would need to be.
Okay.
So, but say I have an address, I don't need to send from my address directly to you in a chain. I could have watch this address, and now you can get another payment from a different address and still attribute it to me.
Okay, because there's some kind of like a secret only you and me share, nobody else.
Correct.
So okay.
So now you can provably say this comes from me because only by my doing a certain transaction or a certain calculation will you receive that other value. And you can have a provable sort of computation that links to that. So now if you get paid on this other account, if you receive Bitcoin, you know that something as a challenge has happened to me, for instance.
Okay.
So Craig does a transaction. You can now calculate an address based on that.
So here, I think I'm trying to understand the big picture here. So what's the usage of deriving like a part of the private key or a key from the UTXO? Is it this
Well,
provable?
one, it increases. it's provable. It increases privacy, and it allows you to do attributed calculations, sort of externally, that you can now say, this machine has done X, I can calculate Y.
Okay.
So if you're a Internet of Things hub watcher, you could be watching for movements from this UTXO set.
Mm-hmm.
It could update you and tell you where the next UTXO you need to look at is.
Okay.
So that information could also be included.
Mm.
And now you can have a set of rules. If this UTXO moves, I do that. If this one moves, I do something else.
Mm-hmm.
This is where I get my updates from. Now, your updates, the keys to do update, for instance, could move to a completely different key that has no linking on the blockchain.
Okay.
And you could say, I will update based on this exchange.
Okay.
And that could even be built into hardware, firmware, etc. Now, what that means is if you're looking at creating a system that's resilient, now the bad guy needs to find you first. So it's not really security by obscurity, but it's sort of more a camouflage principle.
Mm-hmm. Mm.
Now, if there are in IPv6 land quadrillions of addresses out there,
Mm-hmm.
it's going to take years even to port scan something.
Mm. Not
But
probably not
so,
practical.
exactly. If even if they know you're on a /48, it takes a lot of effort and a lot of noise to try and even find your machine.
Mm-hmm.
Even if you're on a home network here and you want to communicate with other machines and they don't know where they're updating, it becomes difficult to find. But each of those machines can go back and update and even provably trace where the next machine will be, even if they've been offline.
Mm.
So online, you now have a calculation that can be done going update to the next UTXO. And you can calculate that path.
Okay. So the UTXO here, so I can see you can be used to derive part of the, I don't know, shared public key or something. But
Yes.
does it have to be part of the chain of transactions involved, or it doesn't have to? So the
No,
UTXO.
it can. I mean, it can be information in script. It can be external information
Okay.
in the UTXO. This is
Okay.
what I'm trying to get people to start thinking about. It can be much bigger than just a little bit of script on chain. It can be entire sort of external processes.
Okay. So it doesn't have to be spent in this type of transaction. Let's say you're going
Not
to send
necessarily,
another.
but if you have a whole pile of external machines that may be offline and only check once a month, and then you'd want to do something like spending and a methodology for calculating in that instance, but that's not always going to be the case.
Okay.
I don't want you to think there's only one solution. I'm trying to get you to think bigger and outside the box.
Mm-hmm. Yeah, because the box I'm in right now is still in a box saying we're like doing some kind of like a handshake off chain, and we're trying to establish some kind of like a common secret. But I can imagine like I think a few classes ago we talked about this like a merchant online, so we can use some kind of like a receipt number or ID, or we can hash it.
Yep.
But I'm still trying to see why do we use UTXO? That's something I haven't fully
It's a
grasped.
verifiable path that you can recalculate.
Okay.
Imagine I've got 1 million IoT machines out there. How do they find each other?
Hard.
I send an update, I make a change, the information's public. And even if they've missed multiple updates, they can go and they can recalculate.
Okay.
And that can even be different for every machine.
Mm-hmm.
So each of those machines can see a different value based on their own key.
Okay.
So that is going to make it difficult for an attacker to try and find anything, but like they find a single IoT device. Well, so what? That's
Because
it. They attack it and an
mm,
individual path.
it's almost like I used to know this kind of like a channel hopping. You want to kind of like
Yeah.
evade some kind of like attacker. They want to jam you, but they only know one frequency.
Yes.
Then the next you go into the next channel. They
Exactly. And you can recalculate and find out where you should be. Even the difference is with most of that, you have to be online at all times and go through where do I go next, where do I go next, and negotiate. But what if we use the blockchain now to negotiate each stage and record something that only the involved parties can know?
Okay, I think I'm understanding a little bit more because if you are like a channel hopping, if you miss one handshake, you're like a lost. You're kind of like a you
Exactly.
lost out of sync. Then you don't know what's the next channel. Then you get lost. But
Yeah.
blockchain here is almost like like a single data of truth. So you can always go there and follow. Even you miss one or two, but you can, because it's deterministic and public available. You can just follow the steps. So you can always get back.
Yeah.
Okay.
So, I mean, where people go wrong is they keep forgetting that software does whatever you tell it to do. It's stupid. There's no intelligence in software.
Okay. AI
So
talk.
if you,
Okay.
I mean, there's no AI. I mean, it's actual ignorance. And if you tell it to do something, it will do it exactly. It doesn't think. So tell it to jump off a building and it will jump off a building. There's no hesitation. It's just, it does it no matter what the consequences are. You can program going, think about these consequences, but you have to think about every possible problem, which is different to people where we can actually consider things. Now, so when we're doing this, we can set up each of these stages. We can say this is the next hop. So some of that can be on chain, some of it can be off chain. But when we're doing this, we can set up how we do key exchanges, how we do addressing. We can even start calculating, for instance, CGA++ addressing schemes, allowing us to update mobile IP and movement of machines around the network over time.
Okay, I think you mentioned this concept quite a lot in the context of IPv6, the CGA. I think it's a cryptographic addressing.
Assigned, yep.
Assigned. Okay, so how does this different from let's say just you get some like almost DHCP assigned IP address?
Because in DHCP you have a single service or group of servers sitting there for everyone to basically attack and take over.
Okay, so in CGA,
DHCP is completely vulnerable, horribly insecure, even on the Microsoft versions of things. Now, with CGA, cryptographically assigned addresses, especially CGA++, if you look at the specifications, there are keyed addressing methodologies that we can now update. And rather than having it trackable, which is one of the weaknesses, we have a way of recalculating new addresses.
Okay, so it is a key, the key part of the whole IP, the full IP address is a function of at least one of the input is a key. Is that a general idea? Okay.
Yeah, but one of the weaknesses I find in all of these is the same keys used forever and a day.
Okay.
So ECDSA has weaknesses when you reuse keys in certain ways. But if you don't ever reuse keys, if you keep key hopping, and what I've said is not the most secure, but you can make that more secure by, as I've been saying, making a HMAC version of it, not one that everyone and their dog can work out.
Okay.
So I've tried to give the very simple, less secure version of, look, this is how publicly you can just calculate where the machine goes. But you can make that more robust by making it more private, by instead of having a public sort of calculation of the number from something as simple as a UTXO, adding some complexity to it, in which case it now becomes difficult to follow, which allows you to do key updates and also redirect people to different addresses. Now, that can also be how your state machine can act in different ways.
Okay.
Remember, finite automata is just a predicate. It is if A, then B, then C, etc. The same occurs when you're talking about different addresses. If I send to address A or address B, and this can be extended outside script as well as in script. So script itself can have multiple external payment addresses.
Okay.
So depending on, like I said, if I make a payment, I do an event. But now I can extend that if I do a payment to A, to B, or to C, I do event A, B, or C. So my machine will watch not only has that payment occurred, but which external address did it go to?
Okay.
And I can calculate values differently. So think about our Diffie-Hellman values again. If you and I share information, then key A, key B, and key C as three different output addresses are going to come up with three different Diffie-Hellman shared addresses.
Yeah, different keys you come up with.
So without adding
address.
the complexity that I keep saying you can do, let's just say S1, S2, S3.
S is the state?
S is the secret, the Diffie-Hellman secret.
Okay.
So from key A, key B, and key C, we now have S1, S2, S3, which is as simple as Shaway key Diffie-Hellman to A, Shaway key Diffie-Hellman to B, Shaway key to C. You can now calculate three different options. And I can now do other calculations and other values to either of those three. So other options can be sent either on or off chains that send additional information to and from machines that can be used either as input or as a value to calculate or as payment.
Okay. Yeah, I think you talk about this kind of like a IoT a lot. So I imagine this is only one of the many application scenarios.
Oh,
it can be
definitely.
Any.
Doesn't need to be IoT. It can be many other things as well.
Okay.
But what we're doing is exchanging information and making decisions, which is all a DFA really is.
Yes, very much.
So we can have a deterministic machine on the other end, look at information based on transactions on the blockchain and act.
Okay. Yeah, it's just a state state can be off chain or on chain, and just the different when you transition, the event can event is from on chain.
So an example would be let's take something as simple as logging into a machine. So the old-fashioned way was a password.
Yes.
Then we moved to things like CHAP,
SS.
challenge.
Challenge response.
Yep, challenge handshake protocol. Now, to do that, there are terrible ways of doing it. The original chap, MS chap version 1, etc., were really terrible. But we can improve it, and that has been improved over time, building the things like Kerberos, Cerebos, depending on how you want to pronounce it, or other similar protocols that we can now even have a record on chain of. So I can do a challenge and without even publicly acknowledging, you can give me information and we can do an update. So I want to access a server.
Okay.
I can do, I won't even go into the ongoing updates of security or encryption keys or access ports or anything like this, but I'll talk in a very high level, not so secure version, just for simple stuff right now. I can basically tell you, knowing where you might be, because maybe I've paid you or maybe I've got an ongoing update of these keys, like I've been saying, and now I contact you saying I want to log in.
Okay.
You can now check whether it's really me.
Because you have some kind of like a, we kind of have a shared common secret, so only you and me know.
Well, no, we can calculate one as we need to.
Okay.
So you and I can mutually authenticate. You can't cheat by being someone else. I can say, I want to connect to you, and you can go, well, I'm going to send you this challenge, which will only be verifiable on the blockchain by both of us, and vice versa.
Okay.
So each of us could, for instance, send part of a payment channel that can be validated, and only if that payment channel for a very small, even single Satoshi token goes through, will it be considered valid on both ends.
Okay.
Now, in doing that, both of us now know, I know that you're the server I want to talk to, because not only can you calculate and validate a message, but I have also been required to do the same. Now, on top of that, simultaneously, I may know that this is Xiaowei key A, but the transactions aren't going to give that away.
Because it's somehow masked with some other external information?
Because we're masking the subkeys. We keep it private. We're not reusing keys. We're not going to do any of that. Now, even the seed that we're doing in a Diffie-Hellman exchange on these new keys is going to be completely new. So if we're using it for encryption and making streams, it's going to be new, and even when we start doing updates, it's not going to be something anyone's going to attack.
Okay, because they don't even know where to attack.
Correct.
So just want to zoom out a little bit. So how is this better than existing authentication mechanism, like I don't know, password or challenging response or even SSH of two-factor?
Okay, so one, we can integrate this into SSH. Two, it is a form of two-factor. So it is a full ability to do challenge response type key systems.
Okay, I think now it's better.
All of the ability to have a client key and a server key in TLS can be there. We don't necessarily need to have PKI, because, for instance, I can now give you a sub key that is trusted because I've paid for the service. The server trusts you because you're the one paying for it.
Okay.
If you set up a Google account and you pay them a small amount, Google knows it's you because you're paying for the damn thing.
Okay.
You set it up at the beginning. You don't need to go out there and validate, is it xiaowei@gmail.com? Why? Because you bought the thing.
Because if it's not you, okay, so Google later is going to, let's say, redirect all the payment to you to that address. So you are
you're going to pay for it initially. You're going to set it up initially. You're going to buy all this stuff.
Okay.
So your access, so your access is based on your access.
Yeah, I could see this definitely. If you are like a bot, you're trying to spam people. That of course, I mean, but if you have extra dollars to throw, I mean, technically you can. It's the same kind of like argument. It's economics secure, but technically you can. In principle, you can do it, but you're just unlikely, very unlikely to do this.
Well, I mean, you can then extend it even further if you want by building an extended version of PKI. So your root key can now be certified by multiple government agencies, for instance. The tax office could say, yes, this is Xiaowei, this is what he pays me on. And chances are no one else is going to want to pay tax for you.
Okay. Yeah, they are more than welcome to, but...
So you can actually build the equivalent of a distributed web of trust, but over all the services that you're doing. This is the key I pay for my rent with. This is the key I pay my tax with. This is the key that I use for my health insurance. And over time, that would even build your identity stronger. So you could base your identity on, this is my passport, this is my driver's license, this is my how I pay my tax.
Okay. Yeah, I don't fully grasp everything, but it seems like you're proposing a better version of like a web of trust, or even better than PKI. You kind of like combine the strengths of both.
Yes, correct. Yeah. So you would look at rather than PKI in an external agency, when you're validating who you are, these are your controls for your keys, and your keys don't need to stay the same. You can have a root key that never goes on chain, that can be tied to a hardware device, that can be on a smart card, that can be issued by a third party if it needs to be, that then can link with other keys. It could even be joint. So I could make a composite identity key that I use, and it could be my IRS key plus my passport key plus my driver's license key. And I could provably,
So does the root key or master key has to be kind of like certified by some kind of like authority, or always, or is it?
Depends on what you want to do. I mean, I can't say always, because if I'm just setting up a random Gmail type account, who cares? Or Paymail potentially. It could be in anything. This is the whole point. If you're going to be validating yourself for buying a house, you're going to want to go into more detail than if you want to go and buy a coffee. If you want to sign up to some competition in Starbucks, you probably want to give them less information than when you're buying a new car, that sort of thing.
Yeah. Okay.
So again, it gives more control to the individual, who can choose how much they want to give in each case.
Yeah, this is seems to me conceptually it's better than either PKI or Web of Trust, because in Web of Trust they're all just like a PGP. They're already just one key, right? If it's just one key, a lot of issues, right? I mean, you pretty much know everything, and also how do you?
It's also then certified publicly and out there so that anyone can check, so that if the CA gets compromised, you're compromised.
Okay, so here is almost like I wouldn't say that, almost like if I may use the word decentralized, like a PKI, it's the everybody
Yeah, we
has
can
their own.
actually take it further. So we can go beyond just this has been my key and have it update over time as well. So if, for instance, I have a new key, I can have the old one recertify the new one.
Mm-hmm.
And all of that can be protected. I mean, there's going to have to be things built in. If it gets compromised, what does it mean? And third parties can say, yes, it was compromised, and say why and update things. But the reality here is uh, there are always options to build in.
Okay. Yeah, it's like if I lose my driver license or passport,
Mm-hmm.
I think I just I can always go to
Mm-hmm.
the government office
Yep.
through some other like a mailing address, I don't know, bank
Mm-hmm.
statement, utility to get it
Yeah,
recovered.
and it could even be done remotely now.
Oh
So.
yeah, I mean everybody says so. So it's
Mm-hmm. Um, so the same with machines. So if we're doing machine-to-machine work, then we're going to want to consider how machines trust each other. And in considering how machines trust each other, we can update keys. Again, our key hierarchy can link to each of these machines. As I've been saying just before, the hierarchy of keys can even be calculated off-chain, and when you come back on, you can then work out where you need to go next.
mhm.
And you can send all the required updates to machines to be able to do uh, how this sort of updates.
Okay. Yeah, just want to just make sure this understanding is correct.
Mm-hmm.
So basically, what you are proposing here is not to have a a complete new version of, let's say, SSH or two-factor. It can be just part of the just improve them.
Yeah.
Just you don't have to build things.
SSH, for instance, allows you to have external updates, external authentication methods. Someone could create a plugin for this. So those updates between machines, the creation of a VPN over SSH, could all be automated
Okay. So from the end
with a
user,
key
they don't
update.
even know. They just log into some server. They say, "Oh, you
Exactly.
need a credential."
I
You
mean,
may
yeah,
already go to Bitcoin or not,
mhm.
but doesn't matter
It
for
could
them.
get information from the Bitcoin blockchain, and they would have no idea it's even happening.
Okay.
Um, as I've said before, it becomes plumbing.
Mm-hmm.
So, uh, what can you do with this? Well, think about what can you do with the DFA? What can you do with finite automata? You can control devices, you can have secure update paths, secure login paths, and at the same time, it can be recorded and saved so that any information that is happening is maintained securely.
Okay.
So if an attack is there, what are they going to find? They're going to get the ongoing calculation um, uh, only to where they already know. They're not going to necessarily know the next value unless they've completely compromised that machine. And then there are ways of, I mean, protecting that by having hardware devices for storing keys.
Mm.
In which case, uh, even the machine may not be able to completely know. So, if someone compromises the machine, someone might be able to integrate while the machine's compromised, but that's it.
But pretty like a SGX or kind of like a secure enclave that
Can be, yes.
even the host doesn't know what's going on inside the
Mm-hmm.
kind of like a
Yep.
blocks. Okay.
Yeah. Which case, um, you flush the machine and start again, and the person has to compromise it again. If there's a vulnerability in the software, they re-compromise it, but if you've patched it, they don't. And meanwhile, it could actually record all the information and send it to the blockchain, in which case unlike the normal attack, the first thing you do is you get on the machine and you wipe the logs, as I've said before. This can be either in an overlay or directly put into the blockchain. If it's an overlay, you can get more data for less money, and that can be secured still, and it can be linked and provably have now all the information that is attributed to this log, which can be rebuilt by someone who's trusted. Now, as an example of how you would rebuild it, think about, do you know about how a transaction log works in SQL? SQL?
Transaction log, no, not. I use
Okay,
SQL,
so,
but not.
All right, so the transaction logs in SQL build every transaction that occurs. If you've got transaction logging, the transaction log is every single update in order.
Okay, append only. I guess so.
Yeah.
Okay.
So it's a log of all the calls. So every time someone makes a SQL update, a call to a table, a update to a table, it's recorded. Now, if you think about that, if you start from the original and you add transaction by transaction, one building block at a time, you get the same output.
Yeah,
so this allows you to rebuild your database even if there's been a corruption.
Okay.
So it's a way of having at point A to get back to point B. But say at point C, the database gets corrupted. Okay. You can analyze what happened and remove that change. So you rebuild the database up to point B, then analyze the extra logs that made the corruption, remove that change that caused the problem, and then continue building.
Okay. Almost like you're like scanning the blockchain transaction to recreate the, I don't know, UTXO set. It's
yeah,
similar.
Yeah. Now remember, we can do this using SPV. So either, and all that can be provably saved. Where I'm talking about overlay networks, you can have a machine out there that captures all of these transactions and even allows you to rebuild. Okay. A machine that allows different machines to react different ways.
So the advantage of using Bitcoin, almost like an anchor here, is because right now I would imagine MyCircle or I don't know, any kind of a commercial data is probably they already have this log. So what are the advantages of let's say using Bitcoin approach?
Security, integrity, the ability to have multiple machines that all react. So it allows us to create individual nodes on a extended network that do very simple tasks. For instance, we could have a machine that goes from state 1 to state 2 to state 3 based on if I get transactions sent at this or this, or let's just say take a state machine with state table 0, 1, and 2. If state 0 gets a 0, it goes back to 0, so it doesn't change. If it gets a 1, it goes to state 1. If it gets a 1 again, it goes to state 2. From state 2, if it gets a 1, it goes to state 2. From state 2, if it gets a 0, it goes to state 1. And state 1, again, if it gets a 0, it goes to state 0. So we have a simple hops between the things depending whether it gets a 1 or a 0. Now, in what we were talking about before, we can have input of just two transactions, A and B. And anytime it gets we see a transaction A, we consider that a 0.
Okay, pretty much encode the input.
Yep. Anytime we get transaction B, we consider that a 1.
Okay.
So that can be now updated either on a payment channel, that can do multiple state changes, or it can now be sort of offline with transactions that are sent otherwise, that we record and update later. We can run through that state externally.
Okay, so the state, I could imagine, could be anything, right? It can be like in MySQL, it can be like a database, an entire database.
It can be that. It can be turning a machine on and off. If we're on state 0, S0, the machine's off. If we're on S1, the machine's in warm-up mode. If it's in S2, it's in full process mode. But we can't go from full process mode to turning off because that will break something. So if we send and it will only accept transactions in that sort of order. So it will go from like external machine can go on, warm up, off, warm up, on, but it can't go from on to off.
Okay.
And even if we try and send it a transaction to do that, it won't accept it because it needs 2 transactions to go from on in our state machine that I've just mentioned to off.
I think, yeah, just my intuition tells me somehow this is more difficult to be hacked because at least the hacker has to figure out at least
well,
why is it spending money?
It's not only sending them a 0 and a 1, but we're sending information on external sort of keys and devices. And we're calculating new keys and devices. Now, the machine doesn't need to be as complex as people think either, because validation is much simpler than the signing process.
Okay.
So you can validate whether something's correct very quickly.
Signing, what do you mean here? You mean key signing?
Doing the actual sending a transaction to the blockchain with a valid signature doesn't need to be on the IoT machine itself. We can verify that and do the signing and control function separate to the machine.
Yeah, could it be like a controller, maybe sending update or something?
Yep. So I can have my big laptop machine here that has the capability to do a signing process that sends a transaction to the blockchain, and an IoT machine that is going between these states, that is very simple, that is hard-coded, difficult to hack because it's in hardware and it's fully verified, and maybe we've actually done a mathematically verified code effort, which rarely happens these days, and it's completely unhackable because we know the state is that well coded, like military missile systems, that this is literally the only way it works.
Okay.
The cost of doing that precludes practically everything ever developed on Earth. There is actually a mathematically verified version of Linux. It's like 15 years behind the capabilities of normal Linux. So it has very, very limited functionality in the real world, outside of a few real-time operating systems that need to be super secure. But this can be done if you wanted to go to that level. Or you could buy a fully verified, already out there machine and just send this and have the updates verified, and that would allow you to have an incredibly secure machine.
Mm-hmm.
So this machine could just wait for the state, and it doesn't need to be super powerful because it verifies what happened. And verification, as I said, is much simpler than the actual signing process. And it's enhanced even further in that it could actually look at the blockchain as an SPV process and see, has this been accepted into a block?
Mm-hmm.
If it's been accepted into a block, this token value now is what I'm going to use to say I go to the next exchange.
Mm-hmm. Yeah, frankly, that's the only case I see like Raspberry Pis can be useful. It's pretty much.
I agree. I mean, Raspberry Pis could be a simple controller that could actually be done on a very secure real-time operating system version of things. I've got for a course I'm doing at the moment at Colorado, I've got I'm doing real-time operating system stuff, which horrible, awful textbook I've got there.
Okay.
Which step-by-step debugging C code is horrible.
Mm-hmm.
So yeah, but this sort of stuff can be done. The hardened Raspberry Pi I've got, which unfortunately I can't take the camera around because it's on my laptop on the fixed one, and Zoom's not letting me change cameras for some stupid reason again. Which is because I had what do you call it, Microsoft's version of stuff, and it seems to lock one camera or the other between the two of them. But anyway, going back to the other thing, the hardened version of Raspberry Pi I've got looks like it is a 1990s nuclear weapon. It's a briefcase with Raspberry Pi stuff and little LEDs and things in the box. You open it up and it so someone's made this thing that looks like it should be a bomb. And if I ever go through an airport, I'm going to basically get frisked.
You don't want to drag that through airport security. I think when I was working at Facebook, we have this some office in Israel. So usually they bring the hardware devices. They have some LED and stuff. Is usually when you go through the security, it's you have to explain a lot because just regular folks just don't bring such things on an airplane.
When I did work in for Mahindra and also for ING Barring back when they existed, I used to travel, and because of the nasty Americans classifying encryption as munitions, going into India was always the word is not fun.
Okay.
Because you would have this declaration form saying that you're carrying weapons, effectively, because it was a munitions thing. So you'd get off the plane and they'd go basically treat you like you were carrying C4.
Okay.
Because the declaration was literally for export of munitions.
Yeah, isn't that just how PGP came out to be? I think the guy he's print either T-shirt or a book. He just flew to Mexico and coming back.
That was one of the things. The people printed it in pages and everything. The T-shirt bit was a bit stupid. The reality is I've got a Maple old programming and Maple book that has all the code. So this is a newer version, but where are we? So the Maple book would have all the how to code it up in Maple, Maple's not the most efficient language, but it's talking about generating 4096 RSA modules, etc., and the seeds, and like the stuff is there, and the original version of all this and some of the C functions goes back way back. Not sure when Maple first came out, but it was old enough. But there were also books like that in C. And in the other room, I've got ones going back to the 80s where they talk about cryptographic functions in C. And of course, when you print it, it's freedom of speech in America. So the irony is you would go and buy a how to code and like do secure coding in C, and you could buy the book and type it in yourself, but you can't buy the code.
Okay. Yeah, that sounds like a intelligent government policy to me.
No, I mean it's one of these asinine freedom of speech means you can type the damn thing out, but or write it, but you can't actually. No hacker worth their salt will ever learn how to compile. Yeah, what can we say? The insanity of all of this. But as I was saying, we can create DFA functions without having to be all in code or all complex. It can be off-chain. So when we're talking about making this more complex than by 0 and 1, remember we're sending state from transaction to transaction 2, provably.
Yes.
So if we're provably sending those state calculations, my external machine can now use a combination of the hash chain that is validated by miners and a transaction stream. Now, if I try and cheat and say that it's outside of this transaction stream, I just won't accept it.
Yeah, I think it's because everything anchored back to the main blockchain.
I mean, remember, I can actually make a machine out there that simultaneously will say, these are the transactions, like an SPV wallet, I will accept.
Okay.
So not only, that's where people go wrong. They think, oh, the miners have to do everything, but they don't. And yes, you might be able to validly send a transaction to somewhere else, but if my machine won't recognize it or can't accept it or doesn't calculate the next address correctly, who cares?
Yeah, pretty much you're wasting your effort.
Exactly. So where I'm talking about sending transaction like to the next calculated address.
Okay.
If that's not going to be calculated by my machine, then what are you bothering with? Even if it's going on chain to a different thing. If I don't, in my software, either on my machine or my wallet, calculate that correctly, who cares? The transaction may still be valid on the blockchain, but my software doesn't see it anymore.
Okay, I see. I think just kind of like a related question, might not be totally in the realm of DFA. I think somebody even asked in the DevCon, I think 2 days ago. So basically, we always talk about this SPV, but where do these low power devices get the headers from? Is that like is this trying to, where's the network that distributing the block headers? So it can be anything, hybrid, BitTorrent, or anything?
It can be anything.
Okay.
So it's verifiable in multiple ways. So do we have one at the moment? Not easily. Right at the moment, everyone's going, the miners need to do everything because they've ignored SPV. SPV does, I mean, I keep making this point. If the hash function is broken, Bitcoin is broken. So if the hash header for a block is broken, the whole block's broken. mean, think about it. The whole block is just a series of hashes, and 2 hashes are less secure than 1. It's something people don't understand. A double hash is less secure than a single hash. So if you have your whole, the hash function and the collisions are broken, the whole Merkle tree is broken, the whole header's broken, there's nothing, there's no security. So either the hash is fine or nothing's fine. So the irony here is with people going, oh, you need the whole block and you need to validate everything. No, you don't. You just need to validate hash header's good, my transaction's good. You don't care about every person being validated everywhere.
So the headers, in summary, basically, we don't have a pretty much a standard way to do it, and it doesn't have to be standard. It's just anything.
No.
It's just data.
Nope.
It can be anything.
It can be, because all you need to be able to do is get a copy of them. Right now, we go out to the Bitcoin miners and go, give me a copy, but it doesn't need to be. It can be a separate network, and we can validate all of the hash headers. We can validate all of the information. We don't need to have every single transaction checked on all of them.
Yeah, I think somebody in the DevCon was joking around even Blockstream satellites they can be distributed the headers.
Yes, you could just use Blockstream satellites and keep pumping them out. 80 bytes is not big, so you could have every 10 minutes. Not only do you send the new one, but you keep streaming out the last 3 months.
Just to be extra safe.
Extra safe, yep.
Okay, then. Right. Anything else as we need to wrap up with this DFA stuff? Any final
That's it for
thoughts?
the moment. So we could probably discuss actually going into how we do more complex automata, how we do set unions, how we create some of these things then afterwards. It can then be mathematically calculated into our addressing scheme as well.
Okay.
Because remember, we can do additive keys. I keep saying that. So that means option 1, option 2, each sort of machine can have a couple states like Q0, Q1, and depending on what happens, the key either goes to version 1 or version 2 of the next state. And if you try and cheat, then it just throws everything and your whole machine's broken. So the hacker tries to cheat and put something out of order, it breaks everything. So follow the path, or everyone knows that you've just broken what you're trying to do and nothing updates.
I see. Yeah. I think just to be play devil's advocate here. So I think what we are discussing here is sounds like to me is more private, more secure. But so the existing method somehow is less, right? But seems the world is still working. So I think that's to me.
I don't know if the world is still working. I've seen so many problems with SCADA, supervisory control and access systems in the past that it's not funny. As an example, a lot of control systems right now, one of the reasons I did things the way I did was they're easily hackable. They're easily breachable. They're based on this concept of airwalling things. No one will get in through my firewall. It's a crunchy shell model. So we can create something that is no longer a crunchy shell. Every system has its own policy, its own connection sort of methodology that, for instance, the control is no longer I connect to this port and then I authenticate you. It's these are the keys. This is the access methodology. It allows me to connect anywhere without even sort of classic firewalls. because
Okay.
I only connect if you're a valid connection.
I see. Because yeah, when we think about this topic, I think I usually think about like a low value target, like my refrigerator or my sprinkler. I mean, you want to hack it, you hack it. But since last week, you know, you probably heard this news. Even a big U.S. Pipeline gets hacked.
I
So
did.
that's probably something you probably want to use extremely secure system like this.
Exactly. And then you could have an update key that takes control back, that is locked in a safe, that is hardware based, that you just plug it in and off you go, access reset.
Okay. Hopefully, if somebody from the pipeline is listening, you know, might be time to upgrade your software system.
All right.
Okay.
Okay. Till next week.
Sounds great. Okay.
I'll start talking about a few extra concepts that Microsoft had, like network access protocol and things that we can build the equivalent of in Bitcoin, but not only for Microsoft, but for anything, anywhere type scenarios, and extending some of these concepts on how to make secure DFAs and beyond next week.
Okay, sounds great.
All right.
Until next time. Okay. Take care.
All right. See you.
Talking. See you.